Go. In chapter 4, we are going to be focusing on a new type of function. And throughout this, or I guess throughout first semester, we only looked at three different types of functions. So we looked at linear function stuff first, which included piecewise and all that good stuff. We talked about quadratics for a whole chapter for like a month and a half, realistically, where we learned to factor and do all that good stuff again. And then we looked at the bigger things, the cubics, where we learned to factor and graph and do all those sorts of things. So chapter 4, we're just extending on that idea, but instead of just talking about those regular types functions, our entire focus is going to be on this idea of rational functions. So when we see the word ratio showing up right here, what we're really looking for is, what's a ratio? Say it again. So a comparison, typically we write them as what? Fraction. So we're looking at stuff that's fractions, essentially. So when we're looking at irrational functions, right off the bat, there's a lot of language here that's going to line up with like science type stuff. And depending on when you took physics or physical science, some of this might seem familiar. But in 4.1, our first section, we are talking about two main ideas. And it's all kind of focused around this idea of inverse variation. Now, for our inverse variation, and this is redundant, and I'm sorry that it's kind of redundant, but I'm just going to sneak in the definition right here, and then we'll run with it. So inverse variation is a way that we can model the real world, and it happens all the time. There's so many different things that are inverse relationships. When you guys think back to physics, or if I think of a stringed instrument, if I make a string, let's say I have a string on a guitar, and so here's just a guitar, it's whatever. Right now, these strings are a certain length, right? It goes from here all the way down to here. That's how long that string is. And I can pluck a string, and then if I push on a fret, nothing changes about the string other than how long it is, right? So now instead of going from here all the way down, if I push here, it's gotten this much shorter. What's going to happen with the tone that comes out of it? It's going to change. How's it going to change? So as the length got shorter, does my pitch go up or down? And that is much higher pitch, right? So we see that there's a relationship. As the length got shorter, the pitch went up, right? And what we see with that very specific situation is a really easy example of this idea of inverse variation. So lots of things in our world relate like that. And there's a couple different ways that we can write these out. We'll say at first, without the mathy version of it, it's simply a relation between two quantities, a relation between, and I'm just going to say two values instead of quantities, only because it's shorter, where one increases while the other decreases. So in that example that we did with the guitar just a second ago, as the length decreased, the tone increased, or the frequency is the real phrase that we would use. Yes, sir? So not necessarily, because if I think of a quadratic, if I pick x gets bigger and bigger, so does y get bigger and bigger. They both go up in that situation. In this case, one gets bigger, one gets smaller. Okay, so when we're looking at this, this is what it really means. If x increases, y decreases, or if y increases, x decreases. They're opposites. Now, in contrast with that, we want the nice mathematical model that we can use for this. And it turns out these models are super easy to define. The model for this, super easy, is simply going to be y equals k over x. This is it. Where this value k right here, and I'm just going to use a different color to kind of point that out, this thing is just a constant that never changes. And it depends on the problem that we're looking at, but if we work out that it's 5 in one example, it'll be 5 for that entire example until we switch to a different situation. Okay, so we can say constant. It's really the constant of variation, and it depends on the field. Like this shows up a lot in physics. If you guys remember ever talking about springs in physical science, every spring has what's called a spring constant, where some value of k determines how strong it is when you stretch it out. That's this constant going on. The longer a spring is, the harder it pulls to come back together. Like that's inverse relationship right there. So we get this lovely model. And the kind of key with these things is when we see it, it is obvious as soon as we read it once that we have something works inverse like this. It'll either say this quantity varies inversely, like you will actually see the word inverse show up in there. Okay, something worth noting, and I'm not going to require that you guys write it down, but if I wanted to, I could take x and y and I could rearrange this. If I multiplied both sides by x, I'll just note here that if I wanted to, I would wind up with this, xy equals k. And all of a sudden, I have a new easy way to check to see whether something is in fact inverse variation. For example, 2 and 3 multiply to be 6, right? But so does 6 and 1, where one of them went up and got bigger, the other one got smaller. And we see that same thing happening. This is inverse variation, and it's a really easy way to check. Now, we're going to do 2 problems right now. One of them is going to be like pure mathy stuff, and then we'll actually see one with instruments and things like that. But let's just dive right in using this inverse variation. So for an example, let's use inverse variation. Cool. Man, my throat's been sore all day, but for the first time this hour, my tonsil is really feeling like it's swollen. Not good. I'd like to take a sick day, but we have like 20 teachers out. That's all right. All right, so for our first one, here's what we're going to be given. X and Y are inversely related. So I hope it's clear, and if it's not, I'm going to make sure it is. What about this tells me it's going to be y equals k over x? There's one word here that I know that when I write this out, I'm going to use k over x. It's this one. Lucy's right. It's the fact that it's inversely related, and we say it right here. Like that's the telltale sign. You might see inversely proportional is the other way that it could be phrased, but you're going to see inverse in there either way. Now, we get a whole bunch more information. What I want us to do using an inverse variation model, and nice job, by the way, Lucy, is I want us to find the value of y when x equals 6 if we're given some information about a different place. We're told that if it's the case that y equals 3 when x equals 10. So we're essentially just given one data point. It's 10, 3, and we're trying to find what is y in this relationship, knowing that it's inverse variation. Okay, these problems, not crazy difficult, but they can be tough to set up the very first time. All we really need out of this is that value of k. Like, once we get k, we're golden. So the fact that x and y, Beatrice, go ahead. So we're trying to find y when x is 6, and we're given this. And that's a great question. If you didn't hear it, why do we have 2 different sets of points given? Well, because we're going to use these ones to find k. So when we're working through these problems, and it doesn't matter if it's like strict math like this, I think that the way that I would separate these out is step 1 is let's find a model and the k value. So find model and my constant k. Now, the fact that we see inversely related means that my model has a very specific look to it. It's going to be y equals what? How do we write inverse variation? If you look up in your notes, when we said it, it said, here's what it means, here's the model that we use. So y equals k over x. That's like our find model part. Now, Beatrice's question is, why are we given this? I hope will become clear here. Do we have an x and a y that we can plug in? Y is 3, so we're just going to plug in, and I'll do a little arrow here so I can save a little space. Plug in. Okay, what are we going to plug in for y? So it's 3 when x is equal to what? 10. Can we solve this for k? Yeah, and it's just one step away, and we immediately see it's just that xy idea. I'm just going to use this implies. K then must be what? 30. So we've done legitimately the hard part of this problem right now. We see that it's inversely related. We write it as an inverse variation or an inverse relation here, and we get our value of k. The only thing that we didn't have in our model was k, because y and x are both variables, which means we now can write our true model. So here's a good rough first step. We just found k, so I'm just going to say therefore, and I'll use those three little dots. We now know that y is equal to 30 over x. So we have a model that we can use at this point. Now, whoever it is, if it's back there, it sounds like it's not here. We just make sure your phone's on vibrate. What are we actually asked to do here, though? Find y when. So now, if we plug in when x is equal to 6, that simply means wherever there's an x, we're going to replace it with what? You're right, whoever is whispering it. Why 5? When x is 6, right? And Kian, you are right. I just want to make sure that you worded it correctly. Tells me that y was what? 5. And look at that. When x is 6, y is 5. And we're done. We have modeled this nice inverse relationship. So it's just, with this, there's no real meaning to it because it's just some value. We're going to do one here in a second where we get real contextual meaning. It just means that if this relationship sticks with it, when x is 6, y is 5. And we can work out more of them as well. When x is 15, y must be 2. It has to be, one has to be higher than the other. As one goes up, the other one goes down. Yep. Okay. So we're going to use a little bit of editing magic. Before we move on, is this terribly hard? What's the dots mean? Therefore. It's just so I can say hey, look, now we get this nice model. Yep. And that's not a me thing, that's a math thing. Okay. They're probably up here somewhere. Yep. Cool. All right. Questions about this one? Because we're going to jump to a very applied problem here. Okay. So I'm going to use a little... So here is the exact same problem that we did before, but instead of just saying it's x and y, we're giving it a real context. We have the frequency is inversely proportional to length. Right off the bat, when I see that very first sentence, I know, and I hope that you know, the model that we can use. Inversely proportional. What is this model going to look like? So y equals k over x is a great first step, but do we have y's and x's here? So all I'm going to do is I'm just going to change the letters. Instead of y, what could we use? We could use s or we could use f. Since I want to find f in the end, I'm just going to write f first. It doesn't really matter which one we put. So I think that my model, if we just try to set it up the same way, is simply going to be that my frequency f is some k value, some constant for this string, over the length of that string. Does that look like the same thing as y equals k over x? Like a little different, right? Because we changed the letters, but it's just because we changed x and y for f and s. Can we find k? Do we have a frequency at some length? So I'm going to give you guys a second. You can grab a calculator if you need to. There's the little ones up here, or there's a few back there. Find me a value for k, and let's see if we all agree with it. Find k first, and I'm just going to say dot, 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 and we'll say k is approximately this, and I want to see if we all get the same thing. Okay, so just to check, in case you're struggling, we have the frequency is 329.63, and that is when the string's length is 26, and this is what I get for k. All right, so now that we have it, we have a nice functional model. I know that the frequency of this string is simply going to be whatever 8,570.38 divided by any given length is. So I wouldn't say it's the hertz. It's hertz per inch, which is a weird idea. It's not straight up hertz. We'll work it out here in just a second. Divided by s, because all we've done is just find k. So this is hertz per inch is what it is. Don't we already know what s is? So only for the first one, we found it with 13, right? Or 26. So now we're trying to say, hey, if I make the string shorter, the frequency should go up or down. Length decreased, the frequency should increase, right? That's what it means inversely. If I wanted to now find the frequency when the string is how long? So 13. So to find the frequency of my new shortened string, we'll just say when s equals 13, the frequency is, and we would just replace s with what? 13. And I have no idea what 8570 divided by 13 is. 659.26. And that is a fairly high pitch. What's middle C? It's like 320, isn't it? Or is it 420, 415? I'd have to look at a tuner. Somewhere in there. Middle C is like 430-ish. So this is a pretty high note, which makes sense, because if it's our middle C string, we make it half as long, it's twice as high. Okay, now, does this make sense that a shorter string led to a higher pitch? Yeah, boom. And we can see it's the exact same math, just used in a context. Okay, seems doable, seems awful. Okay, so we're going to move on a little bit. Do we want a really quick brain break? Let's... Yeah. There's a huge discrepancy between knowing how to play it and how to be good. I know how to play it, but I'm not good. All right. So we're going to hit the second half of this right meow. And what we're going to start talking about is a new flavor of function. We've already been kind of addressing it. We're going to talk and define for ourselves what we will call the reciprocal function. Now, this word, the reciprocal function. Do you guys recognize the word reciprocal? Yeah. What is a reciprocal? What do you do with them? You just flip them, right? You do the hollow, if you will. Yeah. All right. So if I asked, what is the most basic function that you can think of? F of x equals what? X. That's like the most basic, right? So don't sketch or don't write this out. But if I said, hey, give me the reciprocal of this, do you agree that that's really x over some number? It's x over 1. What's its reciprocal? Not just 1. 1 over x. So check it out. That's it. We're just going to say that the reciprocal function, by definition, it's going to be the parent for all of these, and it is 1 over x. Now, all that this does, and you don't need to write this down, but this takes any number, x, and it just maps it to its reciprocal. Are there any values of x that, or any values of any number that we can't divide by? 0. We cannot divide by 0, right? Now, we have not seen a graph that ever does this, I don't think. To my knowledge, you guys haven't. But we're going to check this out because there's some really important stuff that happens with these. And right off the bat, we're just going to think about, I'm going to do some scratch work over here. Anything in purple or pink is just for think right now, okay? So let's pick some numbers. Let's get close to 0. And I just want to see what happens. Like, we're going to make a little table, x and 1 over x. And I just want to see what happens with these values. Give me a number close to 0, Desi. So 1, I'm okay with that. And we'll get closer from there. If I pick 1, what's 1 over 1? 1. Okay, get closer to 0 than 1. So I'm going to call that 1/2. And you're good, 0.5 works. If I do 1 over 1/2, we just multiply by the reciprocal, right? What's 1 divided by 1/2 going to give me? I don't think it's 1/2. So times 2, so it's 1 times 2, it's 2. Let's get closer. What if we're at 1/10? What's 1 over 1/10? 10. What's 1 over 1/100th? So what's happening? As x gets closer to 0, what do my y values do? How close can I get to 0? Can I get closer than this? I think I definitely can. If I can get 1/100th, could I get 1/1000th? And that would be at 1,000 now, right? Or 1/1 billionth, and I go up to 1 billion. As x gets smaller and smaller, y gets what? Bigger and bigger. Now, we see the same thing happen from the other side as well. If I wanted to do the same thing, it would say -1. And we'll just do the same table just with the negative side here. And again, if it's pink, we can just think about it. What if -1? What's 1 over -1? -1. And how about -1/4? We'll switch numbers. -4 and -1/4. 200th. So now notice, are my x's, and this is a weird idea, but are my x's getting bigger? So your gut says you want smaller, but bigger means to the right on a number line. This is the furthest left number. This is a little bit to the right. It's a little bit more to the right because we're getting closer to 0. These are getting bigger. These numbers, more negative, right? So we still see the same thing. X is getting bigger. It's weird because they don't really look like they're getting bigger, but they're closer to 0. They're getting bigger, and these are getting smaller. So we see the same relationship happen. What number can't I plug into this? I can't plug in 0. But what I see happening is as I get closer and closer to 0, my function gets bigger and bigger, right? So what we've just worked out here is an idea of a new word that you've probably never seen. We're going to define for ourselves an asymptote. Okay. My student teacher, when I was student teaching years and years ago, she did not like me. She told everybody that I didn't relate well with kids. Like, she did not recommend me for getting this job initially. Thank God that Mr. Wilson did not listen to her, because I think I relate really well with young folk because I'm hip. But my student teacher, the thing that I remember the most about her is, you might have heard me say this, and if you didn't really pay that much attention, how do you say this word? How would you say this word? Asymptote, right? She pronounced it asymptote, and it has bugged me for years and years. I cannot write this word without thinking of how Miss Myers said this word. Really disliked her. She really disliked me too, so that works out. But an asymptote, it turns out we get one here. We're going to say that this is simply thought of as a line that my graph, or that a function, gets arbitrarily close to. Arbitrarily. So all that means is as possibly close as we want. Close to. And you could just say very, very, very instead, without touching. Okay. It gets unbelievably close to this line without touching. Now, in our next section, we're going to see how to find them a little bit more detailed, but we see that I can get really, really close to 0 here on this table, but I can't ever quite plug it in. And I just want to look and see, if we pull up the graph of 1 over x, can we make sense of whether or not there's an asymptote? So let's check this out real quick. And I'll go back here. Sorry if somebody was still looking. Okay, a line that a function gets really, 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 really close to without ever actually touching it. So let's just check out the graph of that first function. Y equals 1 over x. Is there a line here that it looks like my function, and you've never seen this shape before, is there a vertical line that my function gets really close to but doesn't quite touch? Is it this line right here? Probably not that one. You tell me when to stop moving my hand. Where's that vertical line that we get really close to? Ooh, right here at the y-axis. And it just so happens to be the value that made me divide by what number? If we get to this x-axis, what's that equation? The y-axis. X equals 0, right? If I look at this and I zoom out, it looks like it touches, right? But let's check. If I zoom way in, they don't touch. I get really close to it, but I don't quite touch it. We have a vertical asymptote on this graph. Something that we get really close to touching, but we don't quite actually touch it. Is there something in the horizontal direction that we get really close to, but we never quite touch it? What does it look like it is? What y value am I getting closer and closer to, but never quite touching? I get really close to, but don't touch y equals 0. And the same thing, if I graph it, and I just have that line on there, it certainly looks like I touch it, right? But if we zoom in, do they quite touch? No, I can see I just get really close to it without it. So as we're looking at this graph, we're going to notice something with this. For our asymptotes, they're going to come in 2 flavors for us for now. We have vertical asymptotes, and you will never see me write this word again, I hope, because there's a shorthand that I'm going to use. I assume you guys would use the same one. The vertical asymptote, what do you think the shorthand for this is? If I said, let's find a shorthand for this, how would you shorthand it to be lazy like me? VA. The vertical asymptote. When we have vertical asymptotes, they're always going to be x equals because they're going to be vertical lines every time. And it turns out that in this one, it was 0. And it just so happened to be the value of x that makes me try to divide by what number? 0. If we try to divide by 0, we hit an asymptote. That's what's really happening when we say we can't divide by it, because it goes up to infinity or down to infinity. Like it's not a real number. So we're just going to make a statement here. The x values that make me divide by 0. This is how we'll find all of our vertical asymptotes always. Is there an x that makes me divide by 0? One of the harder parts on your worksheet that I gave you guys last Thursday was I said, here's a function in its domain. Why is this the domain? One of the things that breaks a function is dividing by 0. It's just one of the things that we can't do. Hence, the vertical asymptotes. Now, there also are horizontal asymptotes. And I'm just going to say horizontal without the word asymptote because I think it's implied that that's what we're talking about, where we'll call these ha, just HA. These ones are a little bit harder to pick out, but we will learn the tricks and see how do we find these things really easily. What the horizontal asymptotes really are is just another way to express end behavior for us. And there's some weird things that happen with horizontals, but we'll see that tomorrow. I'm just going to say end behavior. And we'll refine that as we go. So, the vertical asymptotes, they happen at the x's that make us do what? Divide by 0. Like, that is the key. So what that means that we can do is there's two ways that we can approach problems like these. We've already looked at the reciprocal function here, but we're going to see and we're going to work out and try to verify using Desmos here in a moment. I want us to find for each of the following, I want us to find the vertical asymptote, the horizontal asymptote, the domain, and the range. Now, you guys are not going to have to graph functions by yourselves on the homework tonight, just so you're aware. We have like 5 minutes left, and then the rest of it's going to be yours to try to finish the assignment before you leave. But we're going to try to find, for a couple functions, the vertical asymptote, the horizontal asymptotes, the domains, and the ranges, which maybe those are all kind of the same questions. So let's take a look at a couple. And for our first one, let's say that we get this lovely function, f of x equals 1 over, we're going to write it as x plus 2 and x minus 1. Range, R-A-N, I'm sorry. V-A. Domain. Yep. All right. Here we have this beautiful function. Now, there's going to be a couple parts of this that I legitimately think is easier to answer without ever looking at the graph. Even if it's looking at the graph with Desmos, I think it's easier to do it way before then. What number can't we divide by? We just can't divide by 0. Jade, there's a couple of them here, and we're just going to jump right in. If an x value makes me divide by 0, then it's a what? It's a vertical asymptote. So check it out. I'm just going to jump right in. The vertical asymptotes. We can see them from this graph. Jade, only one of them. Is there a value of x that you could pick that would make me divide by 0 anywhere in here? Like if I pick x equals 4, that makes this become 6 times 3, right? That's not a 0 that I'm dividing by. But are there any values of x that would make me divide by 0? Let me rephrase that because as soon as you see how I'm asking it, it's going to be like obvious. Is there a value of x that makes this 0? But if I do that, what's 0 plus 2? Negative 2. If I pick negative 2, it tries to make me divide by 0, right? Is there another value for which that will happen? Negative 1? 1 from this one. Now, here in a second, when I pull up the graph, how many vertical asymptotes do you think this thing's going to have? 2 of them. Now, it's a weird order to do this in, but these are the only 2 places that make me divide by 0, right? They're the only 2 x values that break, quote unquote, my function, which means if we can answer the question about the vertical asymptotes, what we've really just done is answer the question about the domain as well. The domain of this function is all the x's that will work. We've only found 2 of them that don't work. It is really easy to write our domains. I'm going to say it's all x except for which values make us divide by 0. -2 and 1. Every other x value should be fine because it's one of the few things that we have that'll break our functions. Now, the range question is a little bit harder. We'll look at the graph for this one. But let's graph this function and see if it agrees with what we have written here. So I'm going to give it a second. I just looked at the zeros of the denominator. That's how we got these. And let's take a look. 1 over x plus 2. Lost my Desmos. So it's 1 over x plus 2 and x minus 1. Okay, so we'll go back home. And we're going to get some wonky looking graphs that you've never seen before. But I promise there's easy ways to graph these. And it's going to be so much easier. That function right there, it's doing something weird that you've never seen a function do before, I don't think. Are there any vertical lines that it looks like I never quite touch? And it's hard to tell on the graph, but I think I can see one running right through there, right? Do I see another one running right through here? And if I can't tell for sure, and maybe I can't tell if you guys are not giving me tons of answers there, for which reason, but if I plot that line, it looks kind of like I touch it, right? What if I zoom in? I don't touch it. I just get really close to touching it, right? That is by definition what it means to be an asymptote. Where's my other vertical asymptote? At 1. If I graph the line x equals 1 and I turn it on, that green line, same thing. It looks like I touch it, but if I zoom in, I really don't. Now, there's also a plus 2 on the end of it, right? Okay. If we look at this graph, does it appear to be any y values that we never quite hit? And it can be hard to pick out, right? Give me like 30 seconds and we're almost done. This graph, forget about all this. This plus 2, what do you think it did to my parent function? Did it move it up, left, right, down? Up. How many? If the normal horizontal asymptote is at 0, y equals 0, where do you think this one's at now? What did you say? Yeah. So if the normal one's at 0, but I've moved up 2, where do you think it's going to be? Well, maybe. Let's check. If I do the y equals 2, because there's some weird stuff with the plus or minus, remember that changes. But if I just graph y equals 2, I get close to that line, but it doesn't look like I ever quite touch it, right? So what we see, and we're going to refine this as we graph these, but from the graph, we can reason out then that my horizontal asymptote was at what value? 2, and I guess you can't really see it from there. And that coincides with my range. I hit every single y value for this function except what? Only one that I get really close to, but I don't quite touch. Good. So everything except for 2 is all that this says. Now, I'm going to give you guys the next 12 minutes. I want you to work through an assignment. I will throw it up here. Yell if you want to peace out now, you're welcome to. The domain and range part, or the horizontal asymptote part, that's going to be the trickiest, but we'll get through it. The vertical asymptotes, my hope is that that is the easy part. Anywhere that makes me divide by 0 is a vertical asymptote. I just see people still writing. Cool. So I will put this on the Google Classroom here in just a second. For tonight, I want you guys to knock out homework 4.1, which you will find waiting for you on page 187. And I want you guys to try, not 9 through 23, odd. With 10 minutes now, realistically, I think you'll get more than half done. But I'm here to answer questions if it's challenging or if there's issues with it. Cool. All right.